session on finite element analysis. In this session, we are going to discuss about the equations of elasticity which are applied in FEA. Equations of elasticity in the form of plane stress, plane strain and axisymmetric problems is what we discuss in FEA. Elasticity is a branch of mechanics that studies the deformation and stress of materials. In the context of elasticity, there are three common types of problems. First one is the plane stress, second is the plane strain, and third is the axisymmetric problems. The equations governing these situations are derived from the general three-dimensional linear elastic equations. General 3D linear elastic equations. For an isotropic and homogeneous material, the general linear elastic equations are given by, first is the equilibrium equation that you can see here. Now you should remember that we are talking about isotropic, which means the material properties will remain same along a particular axis. Generally, when we talk about material properties, we are talking about the E, K, mu and G. These are some material properties that we talk about, and these properties remain same along all the axes on the body, say X, Y and Z are the three axes. And when I say homogeneous, it means that the material over the entire body is the same and the material distribution is the same. There is no void or any kind of different material which is added into the material. Homo means same throughout the body. The general linear elastic equations are given in three forms. The first one is the equilibrium equation, which is dou sigma ij upon dou sigma j plus Fi is equal to 0, where sigma ij is a stress tensor, that is the force per unit area over the body. Fi represents the body forces and xj are the spatial coordinates. So this is the first equation for equilibrium form. Next we will talk about the constitutive relation. Sigma ij is equal to Cijkl into epsilon kl, where epsilon kl is the stress tensor. You must be aware that tensor is the body forces or strain or stress acting on the body along 4 dimensions. When I talk about vector, it will be along 2 dimension or 3 dimension. So we are now talking about the stress tensor over the body, that is epsilon, and Cijkl is the stiffness or elasticity tensor of the body. The third one is the strain displacement relations. Epsilon ij is equal to 1 upon 2 dou ui upon dou xj plus dou uj upon dou xi. So this is nothing but the strain over the body on the left hand side, and the right hand side you have terms like ui, that is the displacement field, or the displacement is what we are talking about. So ui and j are the two axis. Generally, if you know, in mathematics I stands for the unit vector along the x-axis and j will stand for the unit vector along the y-axis. So here we are measuring the change of displacement with respect to a spatial direction. It is a displacement vector along y-axis and we are considering another spatial change over here. So we are finding the relation between strain and displacement. Now we'll talk about certain specific cases when the case is of plane stress. In plane stress problem, it is assumed that the stresses in the thickness direction are negligible compared to the stresses in the plane, that is along x, y and z axis. That is the meaning of plane. Therefore, the stress components sigma zz, sigma xz and sigma yz are assumed to be 0. So if you see this diagram, Z is nothing but the thickness of the body. So along this direction, we will assume the stresses to be 0. The equilibrium equations and strain displacement relations simplify accordingly. Now here if you see, for plane stress condition, the stresses are given over here. Sigma Z is 0 as we just discussed, and the shear stress along XZ is 0 and shear stress along YZ is 0. But along this XY direction, it is existing. So that is what is given here. Sigma X, Sigma Y and shear stress along XY may have non-zero values. When we talk about the strains, when you're talking about plane stress, but if you talk about the strains along this body, gamma XZ is 0, gamma YZ is equal to 0. Again, you can see it is with respect to Z axis that the values are going to be 0. And epsilon x, that is the strain along x-axis, epsilon y is the strain along y-axis, epsilon z is the strain along z-axis, and gamma xy may have non-zero values. So this is also strain along xy direction, it may be non-zero. Next, we'll talk about the plane strain condition. In plane strain problems, it is assumed that the deformations in the thickness direction are negligible compared to the deformations in the plane. Therefore, the strain components epsilon zz, epsilon xz, and epsilon yz are assumed to be 0. That is again along the thickness direction. The equilibrium equations and constitutive relations simplify accordingly. So you can see here for the plane strain condition, the stresses is shown here. Sigma x, sigma y, sigma z and tau xy may have non-zero values, but tau xz is 0 and tau yz is 0. That's what you can see here. And this diagram is showing some strain along the body. That is along the x-axis and along the z-axis. The consideration of deformation is 0 along the thickness. When you talk about the strains over here, Ez, epsilon z is 0, gamma xz is 0, gamma yz is 0, and epsilon x, epsilon y, and gamma xy may have non-zero values. So that's what we are talking about the plane strain condition here. Now you can see this is epsilon x, epsilon y, and gamma xy. These are the ones which have non-zero values. Now, I have not given you the equilibrium equation and the constitutive relation here. You can also discuss about those equations, and that is what is used in FEA for solving the numericals. Specific cases. Number 3 is axisymmetric problems. In axisymmetric problems, the geometry and loading are symmetric about an axis. The equations are expressed in cylindrical coordinates r, theta, and z form. The strain displacement relations and equilibrium equations are modified to account for the axisymmetric nature of the problem. Now here for this problem, I have given you the equation. So you can see to the left, we are talking about the stress, and to the right, we are talking about the strain. So this is the stress strain relation for axisymmetric element. So here you have the stress along r, z, and theta direction, and this tau will indicate the shear stress. This is the normal stress. And to the right, you have E, which is Young's modulus. This is nu, which is indicating Poisson's ratio. And accordingly, you have a relation here. And these terms are the strain. Next is the usage of axisymmetric formulation for equilibrium equation. This is dou sigma rr upon dou r plus dou sigma rz upon dou z plus sigma rr minus sigma theta theta upon r is 0. So this is one of the equilibrium equation in terms of rz and theta. And you can have one more equation over here which is used. This is along rz direction of stress and zz direction of stress and rz direction of stress with respect to r. So these are the stresses that you can see over the body. So let's sum up the session. The specific equations for each case, plane stress, plane strain, and axisymmetric problems, can be derived by applying the appropriate assumptions and simplifications to the general linear elasticity equations. So, from the equations that I showed you, these equations have been derived. The resulting equations provide a framework for analyzing and solving problems in specific geometries and loading conditions. So, suppose if you're talking about a particular specific condition, say a beam under some axial load, and then you are using a particular equation to solve, then you can use these equations and also give a proper geometry and a loading condition for the beam which is subjected to some sort of load, and then you can get the solution. So with this, I end the session. I hope you understood the lecture. If you have any doubts, please write to me in the comment section. Don't forget to like, share, and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.